Historical background. Part 3. Recent and ongoing advances. The numerous differential equations that resisted solution by analytical means led to the investigation of methods of numerical approximation. By 1900, fairly effective numerical integration methods had been devised, but their implementation was severely restricted by the need to execute the computations by hand or with very primitive computing equipment. Since World War II, the development of increasingly powerful and versatile computers has vastly enlarged the range of problems that can be investigated effectively by numerical methods. Extremely refined and robust numerical integrators were developed during the same period and now are readily available even on smartphones and other mobile devices. These technological advances have brought the ability to solve a great many significant problems within the reach of individual students. Another characteristic of modern differential equations is the creation of geometric or topological methods, especially for nonlinear equations. The goal is to understand at least the qualitative behavior of solutions from a geometrical as well as from an analytical point of view. If more detailed information is needed, it can usually be obtained by using numerical approximations. An introduction to geometry methods appears in Chapter 9. We conclude this brief historical review with two examples that illustrate how computational and real-world experiences have motivated important analytical and theoretical discoveries. In 1834, John Scott Russell (1808 to 1882), a Scottish civil engineer, was conducting experiments to determine the most efficient design for canal boats when he noticed that when the boat suddenly stopped, the water being pushed by the boat accumulated round the prow of the vessel in a state of violent agitation, then suddenly leaving it, the boat behind the water rolled forward with great velocity, assuming the form of a large solitary elevation around a smooth and well-defined heap of water. Many mathematicians did not believe that the solitary traveling waves reported by Russell existed. These objections were silenced when the doctoral dissertation of Dutch mathematician Gaston de Villiers included a nonlinear partial differentiation equation model for water waves in a shallow canal. Today, these equations are known as the the Rice KdV equations. Diedrich Jones Korteweg (1848 to 1941) was the Rice thesis advisor. Unknown to either Korteweg or the Rice, the Korteweg-de Rice model appeared as a footnote 10 years earlier in French mathematician Jean Valentin Boussines's 680-page treatise Essai sur la théorie des équations. The work of Boussinesq and of Korteweg and the Rives remained largely unnoticed until two American physicists, Norman J. Labatsky and mathematician Martin David Glasgow, used computer simulations to discover in 1965 that all solutions of the KdV equations eventually consist of a finite set of localized traveling waves. Today, nearly 200 years after Russell's observations and 50 years after computational experiments of Verbatsky and Kruskal, the study of solitons remains an active area of differential equations research. Other early contributors to nonlinear wave propagation include David Hilbert, Richard Coulomb, and John von Neumann. We will encounter some of these ideas again in Chapter 9. Computational results were also an essential element in the discovery of chaos theory. In 1961, Edward Lorenz (1917 to 2008), an American mathematician and meteorologist at the Massachusetts Institute of Technology, was developing weather prediction models when he observed different results upon restarting a simulation in the middle of the time period using previously computed results. Lorenz restarted the computation with 3-digit approximate solutions, not the 6-digit approximations that were stored in the computer. In 1976, the Australian mathematician Sir Robert M. May introduced and analyzed the logistic map, showing that there are special values of the problem's parameter where the solutions undergo drastic changes. The common trait that small changes in the problem produce large changes in the solution is one of the defining characteristics of chaos. May's logistic map is discussed in more detail in section 2.9. Other classical examples of what we now recognize as chaos include the work by French mathematician Henri Poincaré on planetary motion and the studies of turbulent fluid flow by Soviet mathematician Andrei Nikolaevich Kolmogorov, American mathematician Michael Feigenbaum, and many others. In addition to these and other classical examples of chaos, new examples continue to be found. Solitons and chaos are just two of many examples where computers, and especially computer graphics, have given a new impetus to the study of systems of nonlinear differential equations. Other unexpected phenomena, such as strange attractors and fractals, have been discovered, are being intensively studied, and are leading to important new insights in a variety of applications. Although it is an old subject about which much is known, the study of differential equations in the 21st century remains a fertile source of fascinating and important unsolved problems.